Hello and welcome. Today, we're exploring quantum networks, the very backbone of a future quantum internet. These networks rely heavily on a fascinating phenomenon called quantum entanglement. This is where quantum particles become interlinked, influencing each other instantaneously, regardless of the distance separating them. Entanglement is pivotal for applications like truly secure communication and distributed quantum computing. However, scaling this entanglement to build robust and widespread quantum networks presents significant engineering hurdles. Let's dive into these challenges. First, there's qubit stability and coherence. Quantum information is incredibly fragile and easily disturbed by environmental noise, leading to something called decoherence. Basically, the loss of quantum properties. Maintaining these delicate entangled states of qubits are basic units of quantum information over long distances and for extended periods is a primary challenge. Engineers are experimenting with various qubit platforms like superconducting circuits, trapped ions, and photonic systems, each with its own pros and cons for coherence and scalability. Next up is the scalability of quantum processors and networks. Building large-scale quantum processors with many interconnected, high-quality qubits is a monumental task. Current systems have a few hundred to a few thousand qubits. For quantum networks, the challenge extends to efficiently linking numerous quantum nodes, which might even use different qubit technologies, into one cohesive framework. Then we have quantum repeater technology. Photons are ideal for carrying quantum information over long distances, but they suffer from signal loss or attenuation in optical fibers. Quantum repeaters are essential to extend the reach of these networks by combating this loss without destroying the fragile quantum states. Developing high-performance quantum memories is key here. Efficiently distributing entanglement between distant nodes is fundamental. A technique called entanglement swapping, which creates entanglement between particles that never directly interacted, is crucial for building complex network setups. Current methods can be complex and error-prone, so research is ongoing for simpler, more robust protocols, sometimes even using artificial intelligence. Interoperability and standardization are also critical. As different quantum hardware platforms emerge, ensuring they can work together is vital for a global quantum network. This means standardizing communication protocols and interfaces. We also need to carefully manage how quantum and classical communication channels interact. Despite engineering efforts, errors are inevitable. Quantum error correction, or QEC, aims to protect quantum information from noise and decoherence. Implementing scalable and efficient QEC codes is a major research focus, crucial for building fault-tolerant quantum computers and networks. Breakthroughs in novel hardware are continuously sought. This includes developing room-temperature compatible quantum devices and more efficient photon sources and detectors. For example, Cisco recently unveiled a prototype quantum entanglement chip that operates at room temperature. Integrating with existing infrastructure, like current optical fiber networks, is vital for widespread deployment. This requires developing quantum components compatible with standard telecom wavelengths. Finally, there's security in this new quantum world. While quantum networks promise enhanced security through quantum key distribution, or QKD, the networks themselves must be secured. Developing post-quantum cryptography to protect classical communications related to the quantum network is also important. Despite these hurdles, significant progress is being made. Researchers have demonstrated distributed quantum computing by linking separate quantum processors. New methods for quantifying and generating entanglement are being discovered, sometimes through unexpected AI-driven research. The development of specialized hardware signals growing industry commitment. Predictions for 2025 and beyond anticipate key milestones in hybrid quantum classical systems, advancements in QKD, and more standardized quantum hardware. The quantum computing market is projected for substantial growth. Overcoming these engineering challenges is a complex, interdisciplinary endeavor. Success will pave the way for transformative technologies, all underpinned by the power of quantum mechanics. Thanks for listening.